Since the calculation of the entropy change for the entire universe is a somewhat colossal task, we'll be able to define a thermodynamic quantity from the system's point of view that will allow us to predict spontaneity. That quantity is known as Gibbs Free Energy. Gibbs Free Energy, also known as just free energy, is a state function defined by this equation, where G is free energy, H is enthalpy, T is Kelvin temperature, and S is entropy. For the most part, its units will end up being in joules or kilojoules per mole of reaction. For any process that occurs at a constant temperature, delta G is equal to delta H minus T delta S. We call this the free energy equation, because delta G equals delta H minus T delta S is a bit of a mouthful. Remember that without any subscripts, these quantities will all refer to the system and the system's point of view. If we do some algebraic manipulation and some substitution, we can derive this relationship at constant temperature and pressure. The change in entropy of the universe is equal to the opposite of the change in free energy of the system divided by Kelvin temperature. As a result of this relationship, a process carried out at constant temperature and pressure, like the processes we study in this course, will only be thermodynamically favored if delta G is negative. That's because Kelvin temperature is never negative, so a negative delta G will yield a positive delta S for the universe. When delta G is less than 0, the process is considered exergonic, which is convenient because there's a G in exergonic, and Gibbs free energy is symbolized by the letter G. When delta G is more than 0, the process is considered endergonic, so the reverse process is thermodynamically favored instead. In other words, a process is thermodynamically favored in whichever direction decreases the free energy. That's what we've meant all along by saying that systems will tend towards the lowest energy state. Let's use the free energy equation to quantitatively predict the spontaneity of melting ice at negative 10, 0, and positive 10 degrees Celsius. The standard enthalpy change and the standard entropy change for this process is given, and we'll need to assume that these values do not change very much over this 20-degree temperature range, which is probably a good assumption. Now, to solve this, we'll need to determine the value, and more importantly, the sign of delta G. The temperatures in Kelvin are 263, 273, and 283 respectively, so I think we already know... Wait, look at these units. We won't be able to do the subtraction in the free energy equation without getting them to agree. So let's convert the big one into joules per mole and see what happens. Alright, this just might work. Delta G is equal to delta H minus T times delta S at all of these temperatures. So at negative 10 degrees Celsius, we'll get positive 220 joules per mole, since we'll have to round to the tens place. This makes sense because positive delta G means the melting of ice is not thermodynamically favored at negative 10. But the reverse process, freezing, certainly is favored at this temperature. But then at positive 10 degrees Celsius, we'll get negative 220 joules per mole, which also makes sense because negative delta G means that the melting of ice is thermodynamically favored at 10 degrees Celsius, and we've probably all observed that. But what about at 0 degrees Celsius? Will the melting of ice be thermodynamically favored, or will the freezing of water be thermodynamically favored? What is delta G? Well, when you run the numbers and round to the tens place due to significant figures, what do you get? 0. Yeah, 0. Neither melting nor freezing is more favored than the other at 0 degrees Celsius. And that makes sense because they'd be at equilibrium. When delta G equals 0, the system's at equilibrium. Here's something applicable to many biological processes. It's called thermodynamic coupling. A thermodynamically unfavorable reaction, that's one with a positive delta G, can be paired with an extremely favorable reaction, that's one with a large but negative delta G, to make the overall process exergonic with a negative delta G. This happens when the paired reactions have common intermediates. The conversion of ATP to ADP in cells is extremely exergonic, so it's coupled with processes like activating proteins, the sodium-potassium pump, active transport through cell membranes, and with many other words your biology teacher likes to use. With the free energy equation, we can predict the temperatures at which a process is thermodynamically favored. The key is to realize that it will be at equilibrium when delta G is 0, and will be thermodynamically favored at all temperatures that give it a negative delta G. We will often have to assume that the enthalpy and the entropy changes for the processes do not depend heavily on temperature. As an example, let's look at the vaporization of liquid bromine. For this process, standard delta H is positive 31.0 kilojoules per mole, and standard delta S is positive 93.0 kilojoules per mole Kelvin. Since delta S is positive, but the process has a positive delta H, that means that there will be some temperatures where the fact that it is endothermic will make the process unfavorable. So let's look at the free energy equation again, but we'll solve it for temperature. The temperature in Kelvin is equal to delta G minus delta H all over negative delta S. Or better yet, delta H minus delta G all over delta S to get rid of that extra negative sign. If we substitute in everything we know for this process at equilibrium and adjust for the appropriate units, we'll actually end up with the boiling point of liquid bromine. T is equal to 31,000 joules, the enthalpy of vaporization, minus 0 joules, the free energy change for a process at equilibrium, all divided by 93.0 joules, the entropy of vaporization. This equals 333 Kelvin. That is the temperature that sits right between when the vaporization is exergonic and when it's endergonic. It's the boiling point at 1 atmosphere. So how do we figure out what temperatures will make this process thermodynamically favored? Remember, this is an endothermic process, and endothermicity is not favored. So when is the endothermicity part of the free energy equation going to prevent favorability? At temperatures higher than 333 Kelvin, or at temperatures lower than 333 Kelvin. Well, think back to our Jeff Bezos example. For whom does $87,000 make a bigger impact? The average Joe, or for Jeff Bezos? In this case, it is the lower temperature, below 333 Kelvin, that the endothermicity will keep delta G positive. So it's at all temperatures greater than 333 Kelvin that the vaporization of liquid bromine is thermodynamically favored. That of course makes sense, because 333 Kelvin is the boiling point, so boiling will be spontaneous above the boiling point, not below it. I think that's enough for now. I gotta go.